But if I don't fancy Joe in that way, it's illegal. They're looking for any excuse to put you away. You've got lost, you know. Am I a criminal? Am I a war? Want to decide who lives and who dies? No one else can. I understand. Involving someone I am creating. Some people who have
All right. So that's actually a trailer of a movie called Imitation Games, right? And why did I play that? Well, the story runs around the character called Alan Turing, right? Who broke the German encryption machine called the Enigma, right? And it's called Imitation Games. The movie is called Imitation Games. So Alan Turing is considered as the father of computer science, right? So the computer science or the computers that run today, right, are in a sense, uh, he's one of the major contributors to what we have today, right? So he basically proposed the idea of what's called the Turing machine, right? And I'm not going to go into theory, but just to say that this guy is the one who cracked Enigma, which was an encryption machine that was not possible to crack at the moment, using uh, a device that he developed, which is I would call a computer, right? So anyway, uh, what we look today, today's lecture is basically about organization of a computer, right? Or how a computer is basically built, right? So what do I aim for, right? So hopefully at the end of this lecture, students will be able to explain the main components of a computer, right? So define what is computation, right? Explain the functionality of a computer, what it does, right? Identify different types of computers, and of course describe various components that actually create a functional computer, right? So this term computer, right, comes from the term computation, right? So computation is basically a mathematical term. In a sense, it's a type of calculation, right? uh, that basically can use just arithmetic, right? So it can use arithmetic and non-arithmetic operations, right? And follows a well-defined model, right? So model comes from it typically comes from mathematics, right? So model is something like, for example, if we say uh, like we have a model for talking to each other, right? We don't realize it, but like how do we talk to each other, right? So first, let's say I'm the one who initiates a conversation. I would say something, right? You would listen to it, right? You would think about it, and then you would respond back. When you're responding, I keep quiet and I listen to you, right? So this is a model of communication, right? It's a mechanism, right? If you take two numbers and you add it, right? The process of adding is a model, right? So you take one number, let's say 5, and you have another number 6, right? You add them and then you get the number 11, right? So there's a model, a mathematical model that basically says you take one number and you take another number, you total them, and then what you get is the addition of the two numbers, right? That's a mathematical model. So a math model basically has just like a set of well-defined steps or processes that you follow to achieve some objective, right? So these, in achieving this objective, right, we basically do arithmetic operations. Yeah, arithmetic operations are addition, subtraction, multiplication and division and things like those, right? And then of course you have non-arithmetic. In computation, you have these non-arithmetic operations as well. We call them logical operations, right? Like for example, uh, if you get a GPA, right? A grade point average, right? So you will take subjects, right? And you'll get a grade. You take the exam, and then you get a grade for it, an A or a plus or a minus or a B or a B plus or something like that, right? So each of these grades have what's called a GPA value. So typically, I don't remember offhand, but an A plus or a A has a GPA of 4, right? A B has a GPA of 3 point something, right? A C has GPA of 2, right? So like that, you get a value, right? A numerical value. Now, when you add all of these GP grade points that you get for each of your grades, right? You total them and then you divide them by the number of credits that you've taken in this degree. If you get a GPA above 3.7, you get what's called a first class, right? Now, if we give a computer this problem to find out who are the students, so we give the student the registration number and then we give their GPA, right, in a file or Excel sheet or a database or something like that. And we tell the computer, hey, computer, can you find out who are the students, or we give them the results, right? All the A's and the B's that you got, we give them and you tell the computer, can you calculate who are the students who have a first class, right? So the computer will first see, okay, this student has an A for this subject. So he will get a GPV, a grade point value of 4. He has a B for this subject. So he will get some 3 point something, right? Now he'll calculate all the GPV values. Now he will add them using arithmetic operations, right? Add them and then he'll divide them to find the GPA, right? Grade point average. So then once he has the computer has the grade point average for each student, he will check, is this grade point average greater than 3.7, greater or equal to 3.7? If it's greater or equal to 3.7, so you're asking a question, is this grade point average greater than 3.7? If it's yes, he gets a first class. If it's no, he doesn't get a first class. Right? So it's like a logic operation, true or false. If it's greater than 3.7, it's true. If it's not, it's false. Right? So we do these arithmetic like addition, subtraction, and things like that. And then computation also involves non-arithmetic operations like greater than, less than, equal to, not equal to, right? These kind of operations. So we basically do that kind of thing here, right? So that is computation. And in mathematics, we call it a model. And in computer science, we call it an algorithm, right? In maths also they sometimes call it, but mostly they call it models there. We call them algorithms. So what is a computer? A computer is basically a programmable electronic device, right? Designed to accept data, right? Perform some mathematical and logical operations, arithmetic and non-arithmetic operations at a high speed, right? That's why we use computers, mainly because it is capable of repeating certain tasks over and over again at a very high speed without making errors, right? Because let's say we are given 1,000 numbers to add, somewhere down the line, we might make a mistake, right? But if you give a computer 100,000 numbers to add, it will still add it over and over again, right? And it won't be tired. It will still get the same result, and it won't make any errors, right? But a human, they'll make mistakes, they'll get tired, right? They'll feel bored, they don't want to do it, they take time, right? But a computer is capable of doing this. So that's the main computers for, because they don't get tired, they don't get mistakes, they can follow a program, right? Or repeat tasks over and over again, right? And also do it very, very fast and accurately. So that's why computers we use for various things, right? Various tasks, right? It's just not mm, for day-to-day things like typing letters or using presentations or watching a movie or playing a game or something. But you can use it for research because you will be students in the university, right? You can use computers for various things. You can use, there are subjects, computational chemistry or computational physics, right? Or computational statistics or mathematics, right? Computational biology, right? Bioinformatics. All these subjects are there, right? So you can use these, what do you call, computers for various tasks in various different fields, right? You can use computers in agriculture, right, to monitor areas. Yeah, okay, look at the soil moisture, the pH values, how to fertilize, right? What are the light conditions that are needed, right? How to control greenhouses, how to control air temperature, right? All of these in agriculture, right? You can remotely monitor animals, right, in a farm or something like that, right? Or you can track animals for various zoological or veterinary kind of applications, right? Using various electronic devices, right? Uh, you can, what do you call, use it in medical science. You, of course, use it, right? For example, if you take an MRI scan or a CT scan, or if you take an ultrasound scan, right? Nowadays, X-rays, right? All these medical imaging stuff, right? They use computers, right? Data is stored in computers, right? And now you have actually AIs, right? Or artificial intelligence systems that help you diagnose various conditions, right? So these are all there. So basically, a computer is typically a device that takes in data, does some processing. So the processing actually performing prescribed mathematical and logical operations at a high speed, right? And then display the results. And the results that are come are basically what is we call information. There's a big difference between data and information. So data is basically raw facts, right? Like the temperature over the last, I don't know, 1 year. That is just data, right? If you take this data and plot it according to a graph, right? Or calculate the highest average and the lowest temperatures, right? Or the month, we'll average it and find the monthly average temperatures, right? So a computer will do all this computation like drawing graphs, calculating averages, calculating min and max temperatures, right? Averaging it across months, right? So then what do you have? You have information. You know, okay, typically December and January are the coldest time of the year, right? In Sri Lanka, right? Typical range. Uh, February, March, right? And then August, September can be the warmest time of the year, right? This is information. But just the temperatures is just data, right? So computers taking this data and use processing to create information that actually is useful for the people who use them, right? So that's what a computer does. So computers have basically been analog, right? Like for example, if you were small and you used the abacus, right? Abacus is, I'll just show you one, right? So this is the abacus, right? So this is what they used in China, and kids in China still use this to do calculation. They don't use a calculator; they use an abacus, right? Really fast. They use it faster than you can type on a calculator, right? So abacus was considered as a very uh, old computer, right? One of those things, a machine that does some computation, right? And if you look at this was found in Antikythera, right? It's a Greek province at the time when Greece dominated Europe and North Africa and all of these areas, right? Antikythera, it's a machine. So it's actually you see, it's a set of gears, right? Or wheels that can actually calculate the position of the planets and the sun and the moon and things like that. Right? So it's a calculation device. So it's a computer, right? And then these two machines are, of course, the differential engine and the what's the other one called? No, I forgot the name. Right? So right, they have gears and wheels here, these computers also have gears and wheels and things like that. This basically uses electricity, right? So these use they didn't have transistors at the time, so there were no this gates in a sense. They use these kind of they're called valves, right? Vacuum tubes, and they use these as devices, right, to do certain settings, right? So these, which basically use some physical property like electricity or heat or gear position or right position of beads in a abacus or the position of gears in a rotating thing, right? They're all they have mechanical characteristics, right? And these are called analog computers, right? So we don't use analog computers as such for large scale calculation anymore, right? So the differential engine invented by Charles Babbage, right? I believe this is the differential engine, and this is the analytical engine, right? So what they basically did was, polynomial equations, right? X squared, 3x squared plus 4 x plus 8 is equal to 0, right? Or 3y cubed x squared plus something blah 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 is equal to 0, right? Those are polynomial equations. And what Charles Babbage, right, basically invented, he was British, I believe. He basically invented the analytical engine and the differential engine to solve polynomial equations, right, at the time. So it was a gear mechanism, right, that solve this, right? So for Charles Babbage to do this, he needed some sort of a program, right, to tell the computer, tell the analytical machine how to kind of work. So Countess of Lovelace, right? She was called Ada Lovelace, right? So there is actually was a programming language called Ada. She wrote the first computer program, right? So it was a lady or a female who wrote the first computer program for Charles Babbage's differential engine, right? So yeah, so that kind of tells you what's done, right? But nowadays we have something called digital computers, right? So digital computers are electronic devices that basically have discrete values, right? So what are discrete values? Discrete values is like, okay, for example, uh, if you take current, right? If you take electricity or something, right? It is an analog property, right? So if I take it like this, you will have continuous, that's supposed to be a sine wave, right? You'll have continuous variation. So you can have, if this is zero, right? If it's the zero line, you can have a voltage of, let's say, or a current, I don't know, it depends, right? So let's say current I, right? Let's say 10 amperes. You can also have somewhere down the line, you can have 5 amperes, right? We can also have 5.5 amperes. Just above this, we'll have 5.5 amperes, right? So you can have different values like this. So it's continuous. It can go from negative 10 to positive 10 continuously. So this is continuous. Discrete is something like if you have a 0, you can have either 1 or you can have 0, either 1 or nothing. Right? So you have something like this. So this would be 0. This would be 1. There are no in-between values. Right. So it's like on and off. If you have a bulb switch in your room that turns a bulb on and off, you either turn it on or turn it off. There is no in-between on and off. Unless and otherwise you have a analog controller that controls the current so that the bulb becomes bright or dim, right? But still, it's either on or off, right? It's like true or false. Something can be true, something can be false. There is nothing called in between, right? Unless and otherwise it's a long story, right? So this discrete values, having just one or more values, right, but not continuous, is called discrete. So you can actually have other values as well. Like for example, you can have uh, if this is zero, right? I'll just get a window. If this is zero, okay, this is 25 things. W, right? So you can have multiple discrete values if you want. Okay, so if you have something like this might be zero, this might be one, this might be two. This might be -1, this might be -2. So you can actually have discrete values. So you can have values like this, 1, you can have maybe -2, and then +1 again, and then you can have -1, 0, then +2. Right? So the discrete values will be 0, 1, 2, -1, and -2. So this would be basically 5 possible values. There's nothing in between. Yeah, if you see, there is no 1.5 or 2.1.5 or 0.5 or -0.5. There are no such values. It's either, it's only one of these values, right? So basically, it's in digital computers today, we use two discrete values, true and false, on and off, 1 or 0, right? Positive or negative, right? There is a voltage or there is no voltage, right? This is what we use in modern day computers, right? And we use two values, 0 and 1. So because it is 0 and 1, we call it binary, right? So we call it binary. Bi is like 2. So because you have 0 and 1, we call it binary. So modern day digital computers basically use what's called binary, right? So your computers work on binary. So this data, right? So data that a computer uses, it cannot be used in its raw form, right? For example, if you take a photograph, what is a photograph comprising of, right? It's just a mix of colors, right? In different positions, right? So mix of colors in different positions, various colors in different positions creates an image for us, right? When that image falls on our eye, right, on our retina, in our eye, we see it. Okay, so it creates an image. But this image cannot be stored in a computer. How do you store it, right? So what the computer does is, like I'm just taking an example of image, it goes common for everything. If this is a picture, right, let's say we are looking at a tree, that's supposed to be a tree, right? Uh, eh, this picture is broken down into what's called pixels, right? Like uses what's called, uh, I don't have my writing pad with me today, so it's a bit bad, right? It's called pixels, right? So this is broken down into pixels, and if a pixel is blue color, blue, it creates a value for it in binary. If it's green, it gets a different value. If it gets a different binary value, right? If it's red, it gets another value. If it's yellow or like that, each of these pixels, each of these little dots gets different value depending on the color. So if you take it with a digital camera, the digital camera captures all these little dots and converts them into binary form, right? Converts them into binary form, and then it stores it. When I open this picture on my screen is also little dots. Each of these dots are colored by the data stored, binary data about each of these pixels. So blue will have one binary value, yellow will have one binary value, green will have another one, red will have another one, magenta another, right? Sky blue something, brown a different, black a different value. So all these values are plotted on the screen on each dot in order so that the photograph we captured from our digital camera is now displayed on our computer screen. right? This conversion of these, we call them analog data in the real world. All data is analog, right? This data that's there is converted into a computer data. This process of converting the normal data into computer data is called digitization, because we digitize, convert it into ones and zeros, whatever we have. So it can be pictures, it can be the temperature, right? It can be just text that you and I write or type or something like that, or the words we talk, right? Or the video we grab with our camera, right? Emails, right? Letters, anything, right? That we have, it is basically uh, uh, analog data that we need to digitize so that we can actually store it and use it inside a computer, right? So I'll take another example. You take the example of letter A. How do you store letter A inside a computer? Why do we want to store letter A? In a database, we might want to store a name, right? So let's say the name is Amila, right? So Amila starts with capital A. So then we need to store A, right? We need to store simple M. We need to store I, right? We need to store simple A, L, and we need to store simple A, right? So simple A and capital A in computers are two different letters, right? For us, it's the same, but in a computer, there are two different letters. So how do we store this? We need to store it. If we are uh, typing something, right, and we use the letter A, then we need to, if we're sending an email, then we need to, we want to say hello, Amina, right? We need to convert hello, Amila to digitize so that we can send it over the internet so that he gets an email and he can read it, right? So then we need to convert, digitize A, right? So how do we store this? So there are different mechanisms of storing this. One way is to use 8 what we call bits, right? So what's a bit? A 1 or a 0 in a position is called a bit, right? So if you have a bit, it's a position where you can store either a 0 or either a 1, right? That's called a bit. So that's the basic or the primitive unit of data in a computer. If there is a 1 or a 0 in one position, that's called a bit. So to digitize A, right, using the ASCII character coding, encoding, right? You don't have to worry about this ASCII and all of that. I'm just telling you, it's one way of doing it, right? So we use 7 or 8 bits. So here we have used 8 bits, right? Where the 0th bit or the least significant bit, right? We'll call this the 0th bit, right? And the 7th bit, sorry, the 6th bit. Right? So there's 0, 1, 2, 3, 4, 5, 6 are 1. The 0th bit and the 6th bit are 1. All the other bits are zeros. So we take 8 bits, a space of 8 bits, right? And then in these 8 bits, the 0th and the 6th positions are 1. The rest all have zeros. When the computer sees this, right, or when the computer reads this data, it looks at these 8 bits. It knows it's encoded in ASCII, right? ASCII is ASCII, right? It's ASCII encoding, right? ASCII encoding. It knows that, okay, this is encoded in ASCII. It's 01000001, which is equivalent to A. So it can, when it gets this data and it wants to display it on screen, it will display the letter A because it knows it, right? So this is how data is stored. This is what the data is, right? A is the data, but it's inside a computer, it's stored like this. Okay, right. So now you need to understand how data is measured, because we always talk about megabyte, kilobyte, gigabyte, terabyte. We use these words, right, interchangeably. But what is this, right? So I told you the smallest measuring unit is a bit. It's just one or a zero, right? There is nothing in between. It's either one or either zero, right? So what happens is that if you take ignore nibble, right? Because we typically rarely use nibble. If you take 8 of these bits, right? So this bit you can store 1 or a 0. You take another one like that. Now you can store 2 ones or zeros, right? Now you can store 3 like that. If you take a total, right? If you take 8 bits, that right, that's called a byte. Is in like this, a byte is given like this, a simple B and a capital B, right? If you see a capital B, that means it's bytes. A simple B means we are talking about bits, right? If you take 1024, remember, we take 1024. Why? Because we take 2 to the power, 2 to the power 10, right? Because we are can be 1 or 0. So we take 2 to the power. To the power, because 2 to the power 10 is 1024. Right? So we take 1024 bytes, it forms a kilobyte, a KB. If we take 1024 kilobytes, it forms a megabyte. Megabyte forms a gigabyte, and 1024 gigabytes forms a terabyte, right? And we typically stop at terabyte because petabyte and zettabyte, they are if you're dealing with high performance computing and large storage, right? So we don't go there. Okay. Bit by kilobyte, gigabyte, and terabytes, right? That's what we need to know. So this is for because that's easier, right? Because most of the data is stored in chunks of bytes. Like for example, this is a byte. 1, 2, 3, 4, 5, 6, 7, 8. That's a byte. So ASCII uses a byte, right? Similarly, we always, most of the things we use bytes, we rarely use bits in computers, right? We can, but we rarely, right? Now, data measuring, this is typically for storage. So your hard disk, your RAM, right? I'll tell you what they are, but when you store data, your pen drive, right? Your phone memory, right? All of these are storage issues, right? So we measure them in bytes. Another type of data measure is when you transmit this data, right? When you transmit this data, you have bandwidth. How many bytes or how many bits can be transmitted in a second, right? So now this is very tricky. Here we talk about bits, not bytes. We send 1 bit of data. We don't send 1 byte of data. Then we say 8 bits of data. Bits and bytes. 1 kilobit per second. That means 1,000 bits will be downloaded or uploaded per second, right? 1 megabit per second, right? 1,000,000 bits will be downloaded or uploaded per second or transmitted per second. A gigabit is 1,000 million, right? Terabit is 1,000,000 bits per second, right? So here, previously, it was 10 to the power 2 when we talked about kilo. Now it is 10 to, sorry, oops. It was 2 to the power 10 when we talk about bytes, right here. This was 2 to the power 10, okay, kilobytes. Here it is 10 to the power 3. We are talking, right? We don't talk about 1024. There is a in bandwidth measuring and storage measuring. Here 1024, and that's typically bytes. Here we talk about bits and we talk decimal places. 10 to the power 3, 10 to the power 6, 10 to the power n, 10 to the power 12. Okay, so there is a different difference between the two, right? So if you look at it, you don't want 3G now, no? Or you don't want Edge, right? They are so slow on your phone, right? You want 4G, which is 100 megabits per second to 1 gigabit per second, or you want, if you go near the Temple of the Tooth, the Candy Dalai Maliga, right, or the Temple of the Tooth, you actually get 5G on dialogue, right? If your phone has enabled, you get 5G and you can actually get very high data speeds because it's in testing, right? So that you can go from 10 gigabits per second to 10 gigabits per second, right? So very, very fast data. Okay, so this is just an example of how fast you can actually download a file, right? So if you had a speed of 1.5 megabits per second and you had a 1 gigabyte file to download, it takes you 5,333 seconds to download this. If you had a 1 Mbps line, right, megabits per second line, right, and you had a 1,000 megabits per second line, which is 1 gigabits per second, it would only take you 8 seconds to download 1 gigabyte file, right? So that's the implication of data storage and data transmission, right, or bandwidth. Okay, so let's look at what does a computer do, right? So a computer typically takes in an input. So the input to a computer is typically data. It takes in data, right? It processes it according to a model or algorithm, right? That we've given it. And a model or algorithm, like I said, uses mathematical or arithmetic operations and non-mathematical or logical operations, right? And then gives us an output, which is information, right? So takes in data, processes it, and gives us information. So that is what a computer does. In this process, it can also store data, right? Like, for example, if we type on a Word document, right? Microsoft Word document or OpenOffice Writer document, we type on it and then we save it. So when we typed, it was an input. It processed it and then it showed a nice document on screen. So it gave us an output. When we stored it, it actually stored it in the hard disk or a pen drive or somewhere, right? So we have a storage as well. So computer can not only process data, but it can also store data and information, right? So let's look at an example. So a computer, we want a computer to add two numbers. So let's say our numbers are A and B, right? So since you're science students, you know what variables are, right? You know what unknowns are, right? Like you did X, Y, right? You know what X, Y is, you want to calculate X and Y, what is X and what is Y in an equation, right? So you might want to do that, right? Solving equations, right? In O levels, A levels, you did this, right? So A and B are two variables. We don't know what A and B are. We don't really need to know what A and B are, right now. So we tell the computer, take A and B as input, add them together. So this is the process of adding, right? And then give us the output or show us the output A and B. If you want, you can store it as well. So if A and B is 5 and 6, it will do the addition and show us 11. If A and B was 12 and 9, right, it will do the addition and give us the output 19. Sorry, 21, right? It'll give us the output 21. Okay, so this is a typical one. So this for us is just data. It processes it and then gives us the result, which is output, right? A useful result, right? So data is basically facts or numbers, right? Or pictures or videos or voice or audio files, uh, scan documents, images, anything that you can think of that you can temperature, right? Speed, anything that you can think of, right, is data, right? Those days, the biggest problem was we weren't able to capture data, right? Like for example, if we wanted to count the number of vehicles on Peradeniya Road, right, you have to stand there, right, for a whole day if you want to count the number of vehicles passing through on Peradeniya Road for the whole day. You have to stand there and then you have to count. One vehicle, two vehicles, one car, two bikes, three tuk-tuks, right? You have to count. Very, very difficult, right, to do. So you have multiple people doing that. And if you have to collect data over 1 year, if you want to, let's say, plan Kandy city, right? How to plan it when if you're developing it, you want to count vehicles, right? Where they enter, where they exit, all this has to be done. Now it's very difficult because we didn't have the sensors. Our sensors were like humans had to stand and wait, count. Nowadays, what do you do if you want to do that? You fix cameras at different points of entry onto Peradeniya Road, right? So one at Gataway Junction, one at near the police station in Kandy, another near Mulgampala, right, where you have the near Kingswood, Mulgampala, right, Hirasagala intersection, right? There you have cameras, right, and one may be coming from Manivatta side, right, and all these. You have cameras, and then you capture this data. Right? So people from not from Kandy must be wondering what is this fellow muttering? I don't know, right? Okay, when you come to right. So now you have cameras. The cameras these roads, right? The computer gets these data from the cameras. It'll identify number plates and it'll know where did this car enter, where did it exit, right? So it can map what did this car do, how long did it take to come from Peradi near the police station in Kandy to the Gatame Junction. So you know the speed. If you calculate it for multiple vehicles, you get average speed, right? You also get routes of what vehicles take, right? You get a count of vehicles. You get what type of vehicles, right? All of these can be captured just by having cameras and a computer, right? So all this data that you're capturing, images of vehicles and vehicle number plates and all of that, it's just data. When you process them, right? When you process them, okay, this is a car. You identify a car. You increment the car number of cars. So you say, okay, 1,500 cars passed this place between 6 in the morning and 12 in the afternoon, right? Uh, Another 800 cars passed between 12 in the afternoon and 6 in the evening, right? So you can have basically counts, right? You can have counts for this, right? So when you do this counting, averaging, clustering, or how many number of three-wheelers, how many bikes, how many cars, how many lorries, how many buses, right? What was the average speed? When you do all these calculations, now a person who wants this information will look at it and say, okay, so most of the cars coming into Kandy or the vehicles coming into Kandy are cars, right? And this is the average speed during this time of the day, right? So now we have to figure out, okay, how do we solve this problem? Where do they come from? Can we increase the number of buses, right? Good buses where people can travel without sweating and bumping into each other, nicely seated, so that they can go to office and work without having to have a bath before they go to work, right? Can we do this? Right? So you can make decisions like that. To make decisions like that, you need information, and that is what the computer gives. It takes the video data, converts it, right, into some form of information that is useful, and then the people can make decisions based on that. Right? And to tell the computer how to do this, right? You see, a computer is a dumb machine, right? As I use the term dumb, as in it has no brains, right? It has no brains, it can't do anything unless and otherwise you tell it how to do it, right? You tell it how to do it. How do you add two numbers? You have to tell the computer how to add two numbers. You have to ask the computer, okay, how are you going to identify the number plate, right? How are you going to do that? How are you going to identify the number plate, and how are you going to three-wheeler or a bike or a car or a lorry, right? How are you going to uh, count them? How many cars, how many three-wheelers? You have to tell the computer every single instruction on how to do it, right? You can't just tell the computer count cars. It wouldn't know how to count cars. You have to tell them go to the RMB website, right, or the surveys, find out whether it's a car or what it is, right? Then add it as a car. Or else you say, okay, using AI, you say, okay, identify, this is a car. These are what cars look like. Okay, now this is the video, count how many cars. So it will look at things. So, okay, this looks like a car. Okay, car. This looks like a bus. This is a bus. So 5 buses, 10 cars, right? 3 motorbikes, 5 3-wheelers. So it will do this counting. But you have to tell it everything, how to do it exactly. This telling the computer how to do something or giving a sequence of instructions in a language that the computer understands, so we call it a programming language, right? To perform some useful task is called a computer program, right? When you give this sequence of instructions, right? Writing these instructions is called programming, right? So if you're thinking of taking computer science as a subject in your undergraduate, thinking of or writing instructions to the computer on how to do something is called programming. So writing a program is called the process of programming, right? So the next thing we look at is types of computers. We don't need to go detailed into this, right? So the most powerful computers in the world today are called supercomputers, right? IBM has them, US Department of Energy has them, right? NASA has them. There's one in Switzerland. There's, I think, one in Russia, in China, in Japan. There are a couple, right? In China, there are a few. These are extremely costly but extremely powerful computers. Your computer might, or the computers that you have access to, might take I don't know, maybe 1,000 years to solve some problem, right? It can be a computer might take that long to solve a problem, 1,000 years. A supercomputer might be able to solve it in less than a day, right? So you can imagine how powerful these computers are, right? 1,000 years, so 1,000 into 365, right? So 365,000 days, right? It might just take one day or a few minutes to solve it, right? If you look at computers that are used in, for example, banks, right, or the servers, you might have heard the word server, right? In places like universities and things like that, they are more or less these mid-range computers, right? They are still about 10 million Sri Lankan rupees or something like that, of at least 6 to 10 million Sri Lankan rupees, right? That these computers are, yeah, relatively still expensive compared to your or my computer. But if you take a supercomputer, even countries can't afford them, right? An entire country can't afford them. That's why you have so few in the world, right? But the typical type of computer you and I use are called microcomputers. Right? Microcomputers are what are called personal computers because they are used by you and me. So they are used for personal, right? Typing letters, playing games, watching movies, downloading, browsing the internet, right? Doing some programs, right? Editing videos and movies and music and things like that. That's all done on personal computers, right? Or PCs. They are also called microcomputers because they have what are called microprocessors, right? So you must have heard AMD Ryzen, or you must have heard Intel i5 or i3 or i9, right? 13 generation, 14 generation processors. You must have heard of these terms. They are all microprocessors, right? Or micro chips, right? So these are what run on the computers you and I use. So this is the typical view of a microcomputer that we have, right? A monitor, keyboard, a mouse, and a CPU. I don't know what to call it, a PC, right? But ubiquitous, they are everywhere, right? You don't even notice that they are around. So these microcomputers, they might come as in a desktop, right? So I've chosen the Apple range for one simple reason: they have the whole range, right? So they have the desktop, right? They have laptops, they have tablets, they have smartphones, they have smart watches, and then they have these, what do you call them? Like you have Google and you have Alexa and these kind of things that kind of are in the middle of the home. They control your lights, they control your TVs and your windows and refrigerators and all of that, right? Uh, I forgot what they call, right? So you have all these devices, all of them have microcontrollers or microprocessors, right? And these are all these devices are now called microcomputers, right? Or personal computers, right? Even your smartphone, right? So if you have a smartphone, right, like a Huawei or Samsung or Vivo or Apple or anything, right? iPhones or anything like that, they are all actually computers because they can do uh, what my first computer couldn't even think of, right? So the first computer I used had something like 8 megabytes of RAM, right? 8 megabytes of RAM, a 1.2 gigabyte hard disk, and a processor that works on single core, 166 megahertz, right? 166 megahertz. Nowadays, computers work at 4.7 gigahertz, right? So 4 times and 1,000 times. So 4,000 times faster than the processor I used, right? Back in 2002, 2000, yeah, 2001, 2002, right? Long time ago. Yeah, some of you all were not born. I don't think you all were born, right? Uh, and the memory nowadays, like I had 8 megabytes, right? Nowadays you have eight gigabytes is the standard, right? So you have 1,000 times more memory, right? Hard disk space, now we have terabytes. I only had 1.2 gigabytes of hard disk space, right? Pen drives didn't exist, right? We had to use what are called floppy disks that could only store, uh, what was it? 1.44 megabytes of data, right? 1.44 megabytes of data. Taking a movie home wasn't possible, right? You had to take thousands of floppy disks if you wanted to take a movie home, right? So you can't, that doesn't work. Okay, so yeah, so computers have developed so much over the last 20 years, right? That they can almost do anything now, right? So Microcomputers, right? So your desktops, your tablets, your notebooks, your laptops, your smartphones, palm tops, right? They're all uh, they have these microchips, right, which are called microprocessors. And you might be interested in, we also have something called embedded computers, right, which are in various appliances and various devices. Like, for example, nowadays, cars have a computer, right? It's called the ECU, right? Or a part of it, but typically a car has a computer of its own, right? If you take certain washing machines, right, machines that wash clothes, they have micro computers, right? If you take your TV, right, TVs are smart now, so you have smart TVs that can browse the web, play games, videos, right, connect to the internet, I don't know, do various run programs and do various things, right? And refrigerators that will send you SMS saying that you don't have eggs in the fridge or you run out of milk, right? These kind of things. So refrigerators are smart. Okay, it will show you the morning weather and the news on a screen on the refrigerator, right? So these devices are all they're embedded because they are devices that have the computer embedded into them, right? So they're called embedded computers. In addition to that, you might also be interested in what are called single board computers or SBCs, right? Which are also microcontrollers. So Raspberry Pi or Arduino, right? Or these are some of the single board computers. So you will see you can have a network, you can have USB, you can have sound, you can connect other devices, right? Like sensors and all of that can be connected to these boards, right? And you can write a program and store them in this program, right? If you have a water tank at home and you want to control the water tank, right? You can write a program for this, right? If you have I don't know, if you have fruit trees in your garden, right? Okay, if you have fruit trees in the garden, when the fruits ripen, the bats come and eat them, right? So you have to either tie what we call those days, we used to call it a take, right? You tie it in the tree, and then someone in the night has to keep pulling it, right? But imagine if you can take one of these boards, right? Have some kind of sensor, maybe a audio sensor, right, or a IR sensor to detect bats, right? Detect bats and automatically activate some motor or something that will make a sound, or right, or speaker or a loudspeaker that will make some sound, right? That the bats will get scared and fly away, right? So you can use these devices. So you can have sensors that do that, right? And then you can connect speakers and things like that so that you use sound to scare away the bats, right? Same goes for, I don't know, we have a big elephant human problem, right? Conflict. How do we detect elephants? Big problem, right? Because you use drones to detect elephants. Sometimes a big rock is also detected as an elephant, right? Or an elephant is detected as a rock, right? You have problems like that, right? How do you know when the elephants are going to come, where they are going to come? Right? Can you detect that? Can you build a device? Some use these elephant collars, right? So it's like a collar around the elephant with one of these devices with GPS trackers. But then it's a burden for the elephant. And then the battery runs down. You have to tranquilize the elephant, put in a battery. Right? That's also not good, right? So you have things. How do you detect this? Can you come up with a? These are the problems that you as computer, you as what do you call science students have to solve, right? How, like a student taking zoology, right? The student taking zoology can work with either students in computer science, or you can work with a supervisor in zoology and in computer science or computer engineering and come up with a solution, because computer scientists don't understand how elephants work. Zoologists understand how elephants work. So if you can bring that expertise, and you can do a third year or fourth year, third year or fourth year project, research project. How do we identify elephants? Right? Can you use ultrasound? Right? Not ultrasound. What is it called? Infrasound. Right? Elephants have a very low pitch. Right? Can we use infrasound to basically identify elephants? Can we build a device? You all might not know have the knowledge to build the device, so you come and talk to someone in computer science, right, or physics, right, because they know about infrasound and ultrasound and all of that. You talk with them, and then you find a solution, right? Just running behind counting monkeys in zoology or counting plants, right, or just writing a computer program that does something, right? They are not the real thing, right? You have to solve problems that are there in the world, or especially in Sri Lanka, right? Because the taxpayers, right, your parents, right, we, everyone is paying tax. That is what the money is going to help you study for free. We call it free education, but it's actually not free. Someone is paying for it, right? So you all have to think big, solve problems that are there in the world, right? And computers are one of these devices that bring solutions to problems, right? Or can be used to solve problems in the world, right? In the country. Okay, so you all have to think big like that, right? If you're a scientist, you all have to be real scientists, not just get a certificate, BSc honors in uh, computer science, or BSc honors in mathematics, or BSc honors in physics or chemistry or zoology or botany or geology or anything, and just go out and then I have a degree. Anything, it's pointless, right? So you have to learn, not just to get a certificate. You can go anywhere and you can even buy a certificate. You can buy a degree certificate if you want. Okay, but here you are here to learn, and you should use that opportunity because someone is spending money on you, right? Try to solve problems that the people have, right? Okay, so if you look at computers, right? So this is called the von Neumann architecture. So you have a device which is called the CPU, or the central processing unit, that takes in data, right, as input. So you have devices that input data to the CPU. It will store it in memory for a short time, right? Like, for example, if I tell you add 9 and 10, right? I'm telling you, so add 7, 9, and 10. When I tell 7, 9, and 10, you hear it with your ear, memory for a very short time, right? 7, 9, and 10 is what he told me to add, right? So then what you'll do, 7 and 9, okay, that is 16. Okay, now 16 you store in your memory for a very short time. Add 10 to that, 26. Okay, so 7, 9, and 10, when you add them, the answer is 26. Right? And you will tell it with your mouth, okay, the answer is 26, or you will type it in the chat saying 26. So you, as a human, your ear was your input device. You heard what I said. 7, 9, and 10 has to be added. You converted what you heard, 7, 9, and 10, and you stored it in your memory. Right? Then you added them using your brain. Right? Use your brain and you added them. Right? In between, you stored it. So you added 7 and 9, and you said, okay, 16. Then you said 16, and then you knew 10 was there. 10 and 16, you added 26. And then you said, okay, the answer is 26. Now you said that out loud. Right? You output. Exactly, the computer architecture follows what a human does. It takes in input, processes it, maybe stores it for a short term, and then gives an output. Right? This architecture is called the von Neumann architecture. In addition to that, if I told you next week's lecture is on Monday, 9 to 11. Is it 9 to 11? I don't know, right? You check your schedule. I'm not sure, right? If I say next week lecture is Monday 9 to 11, on Sunday also you'll remember that, right? Because I told you. Why? Because I told you add three numbers. If I ask you what were the three numbers, some of you will remember, some of you won't. So the numbers were 7, 9, and 10. If I ask you tomorrow what the numbers were, you wouldn't remember. Even I wouldn't remember most likely. Right? That is because you only stored those numbers while you needed them. So you store it in your memory, temporary memory. But in the long run, like lecture on Monday, 9 to 11, if I say that, you still remember it on Sunday and even on Monday, right? 4 days or 5 days later, you are still remembering. It's like your hard disk. You stored it in your long-term memory. So the computer architecture kind of models what humans really do, right? They have sensors like their eyes, their ears, their skin, their tongue, their nose that takes in input, right, from its environment, does some processing, and then acts on it, right? You can act with your hands. Actuators are your hands, your tongue, your mouth, your eyes, your face, right? You shake your head no, to say yes and no, right? And those are all actuators, so you can have a right? So we look at what are the inputs of a computer, right? So what are the devices that help input information and data into a computer? What are the outputs? What does memory look like? Or what are the types of memory that we have and what are the storage that we have? So we look at these components. So this environment has what we call hardware. Hardware is something that you can touch. So if you have a monitor, you can touch it, right? If you have a keyboard, you can type on it. If you have a mouse, you can move it around, right? If you have software like Microsoft Windows, right, or Linux, or Microsoft Word, or Photoshop, can you touch them? No, you can't touch them. They're not physically there. All the parts that are physically there in a computer are called hardware. They can be felt, they're hard, right? So they're called hardware. The programs that run in your computer, right? Like the operating system, Windows operating system, or Linux or Mac OS, Android on your phone, right? iOS on your phone, right? PowerPoint, or Word, or Excel, right? Photoshop, the games you might play, the web browser, all of them, you can't touch them, but they're inside your computer. They're called software, right? The data you feed that is displayed on the screen, that might be stored in the hard disks, that is on a paper that you're entering, right? These are all data, right, that are fed into the computer. So the computer has hardware, there's software that runs on the hardware, and then there is data that you feed in, right? And the people who use them, right, are the users, right? So we have hardware, which are tangible, which are can touch, software that are basically programs or electronic instructions, data that are raw facts that can be either inside the computer or it might be in a paper or something like that. And then you have users who are also called liveware because they're alive, right? They breathe and eat and drink, right? Like you. So they're called liveware. Okay. So what are these hardwares? They're these tangible computers. And these components typically can be listed as the main component is called the central processing unit or the CPU. right? The CPU is basically the brain of the computer, right? The brain of the computer. This is the most important part of the computer, right? The main memory or the memory is what stores data, right? That you're using in the computer, right? We call it primary memory, we call it main memory. Some call it RAM, random access memory, or RAM, right? That's the common term that we use. In addition to that, we have devices that are in the periphery of the computer. So the central processing unit is the main thing. The main memory is connected to that. In addition to that, you have peripheral devices or devices that are called input and output devices, right? And also communication devices. And then fourthly, you have what are called storage, right? Storage is where you store your data, right? So I'm not going to go into these things, right? I think if you all get computer science and you take CS 101, I might touch on these, right? What these are. I won't touch on them in this course, right? So the brain of the computer is called the CPU, right? Some call that big box like thing, they call it the CPU. That's not the CPU, that's the outside is the casing, inside you have a motherboard. On the motherboard, you have the CPU, the RAM, right? The hard disks connected and all of that, right? And the power supply. So that's actually not the CPU. Some just call it the CPU, right? But the CPU, in technical terms, is this little microchip, right? Or microprocessor that is the brain of the computer, right? And this is what actually does the processing because it's the brain, right? It's like a human brain, right? When you think, when you do calculations, when you do anything with your brain, you're thinking, you're calculating, and things like that. You're processing the data, right? That's like your brain. In addition to that, your brain also manages your body, right? Whether you open your eyes or close your eyes, or you turn your head, or you run or jump, or you sit or stand, right? All of these are controlled by your brain. So what does the processor do? It actually does a similar thing. It processes data, right? It also manages all the components in the computer, right? All the devices are managed by the processor. Uh, so what is a processor made out of, right? Or what are the components of a processor? It controls all the devices. Then the keyboard can send a message, the mouse, or how to move, how the mouse pointer will move, can read and write, right? When the what do you call, when data can be written to the main memory and when the data can be read from the main memory, who can use different parts of the computer, and all of that is controlled by the control unit, right? The second unit is called the arithmetic logic unit, right? So this is where all the calculations happen. So here, if you look at, remember this, we know one part controls all the devices, all devices. So it's called it uses the control unit. Actual is actually doing the computation. That is done by the arithmetic logic unit, right? Or the ALU, right? So addition, subtraction, checking whether something is greater or equal to or smaller or larger, right? All these operations are done with the logic unit. So that's called the ALU. And the third unit, or the third part of the computer is called registers, right? You see, this is your main memory, or we'll call it, for now, we'll call it RAM because that's what the word you know, right? This is called the RAM. Now the processor has to write to the RAM, or read from the RAM, read and write from the RAM. The RAM is not on the processor. You have to use what's called a memory bus, right? Or a data bus to do this, right? So this bus that you read and write from the RAM is relatively slow. It's not really slow, but it's relatively slow, right? But sometimes you need data, like if you're adding 5 and 6, you need this data that you're immediately going to need to do some calculation on the CPU. If it has to be read from the RAM, it takes a while, so it gets slow. But if you can load the data that you immediately need, right, and keep it somewhere on the CPU, right, that's very useful, because the data on the CPU or the memory on the CPU is extremely fast, right? You must have heard of this as cache, C-A-C-H-E, right? So you have different levels of cache. You have level 1 and 2 cache that is on the CPU, right? You also have uh, level 3 cache, which is called shared cache, when you have multiple processors, right? Or multiple cores on the single processor, they are called level 2 cache. But even faster than this cache, right, is what are called registers. They're extremely fast and directly connected to the ALU. So data that you immediately need is stored on registers so that you can easily use those data, read and write those data without slowing down at all, right? So that component which stores data that is immediately needed are called registers. Okay, right. So this is just an explanation of what I was mentioning. So memory typically can be classified, right? So computer has memory, right? Memory can be primary memory like your RAM or something, or your ROMs. It can be secondary memory. Tertiary memory, we don't use it that much now, right? And offline memory also we don't. This we use it as in your pen drives and your CD-ROMs and all of that, right? So primary memory, right, can also be categorized into two types. One is called read-only memory. You can only read from the memory, you can't write into that memory, right? That's called ROM, right? Read-only memory, so we say ROM. Right? Now, this memory is quite interesting. You see, when you turn off the computer, you don't want to lose some of the programs. You don't want to lose some of the programs. But the problem with read-write memory and other memory we typically call RAM, right, is if the power goes off in the computer, so read-only memory data permanently, right? Now, what is this? Like I told you, computers are dumb machines, right? They can't do anything without us telling how it should be done. So we tell the computer how to do something by writing a program, right? Telling how the computer to do something also includes telling how the computer to start, how to turn on. When you press the button, a signal goes to the computer, right? And on the computer, there is something called a ROM. Some call it a BIOS chip, right? Some call it a post test, right? Power on self test, right? All these things, right? A program is stored on the ROM of the computer because you don't want it to get erased. Because if it did erase, next time the computer can't start because it doesn't know how to start. It doesn't have the instructions on how to start. So this program right? The startup program of a computer is stored in this ROM, right? There are different types of ROM, right? What do you call flash ROM is the type you'll get in your pen drives, right? Or USB sticks. They are flash ROM. Electronically erasable and programmable ROMs are what you get in current computers, right? Erasable programmable ROMs are what you used to get, right? These are programmable ROMs, read-only memory, where they are actually made itself, right? You can't, right? So this is even they are made as a blank chip. You can write a program. This is you can erase and write. So to erase, you use some ultraviolet light, right? This is you can electronically erase and program, and this is typically your pen drive kind of thing, right? So the program to start up the computer is typically stored in a memory. So it tells you, okay, power up, check whether the keyboard is okay, check whether the CPU is working, whether the memory is all working, right? See what the devices that are connected, right? Then load the program from the hard disk, right, or a CD to start the operating system. All these commands are stored in your read-only memory, right? ROM chip. So these are some of the ROM chips, right? So this is an electronically erasable programmable ROM, right? This is an erasable programmable ROM. So you see this little window, you shine ultraviolet light on this, it erases the chip, and then you can write a new program, right? And these are programmable ROMs or PROMs, right? So this is a PROM, this is a EEPROM, and this is a EPROM, right? So ROMs are non-volatile, which means they don't lose their information when the power is turned off, right? And they're basically on the main ROM on your computer is on the motherboard, right? Sometimes called the BIOS chip. Right. Then we move on to what we call RAM, right? Or random or primary memory, right? What you and I typically call RAM, right? And what we call RAM is actually DRAM, dynamically access memory, right? So our memory can be accessed from any location, right? So we call it dynamically accessible. This is called sequential accessible RAM, and this is content accessible RAM, right? Dynamic, sequential, and this is content. These two are not very much used. DRAM is what you and I use, right? Or dynamic access memory is what you and I use, and that is what we call random access memory, right? So this is what a random access memory looks like if it's a desktop. If it's a laptop, it looks like half this size, right? And nowadays they come soldered onto the laptop itself, so you can't change them, right? Now the thing with RAM is, if you pull it out or you take the power out, it loses the data. So it's called volatile, right? Wow. The data disappears if the power goes off, right? So RAM is not good for storing permanent data, right? You only use it for storing data, information, and programs that are currently being used by the computer, right? Because once you finish, like for example, you are typing a Word document, you forgot to save it, and your little brother or sister came and pulled the plug. You lose all your data. All the stuff you did on the Word document is now lost. Why is it lost? Because it was on the RAM. We didn't save it. When we save it, what happens? it goes on to a secondary storage device. Right? So it stores in a hard disk or a pen drive, right? Or a memory card or a CD or somewhere, right? So if you want to store data for a long period, right, over time, we have to store it in a hard disk, which we call HDDs, right, or solid state drives. Now your computer disks also come as SSDs, right? Now the difference between SSDs, right, and hard disks are about, if I'm not mistaken, 25,000, 2,500 times or 25,000. I've forgotten, right? So if the hard disk, if you have a hard disk in your computer and it takes you 3 minutes for Windows to load, right? Your SSD might only take something like 10 to 15 seconds, right? Much, much faster. So they're called solid state drives. They are not mechanical. Hard disks are mechanical. They have a motor and they have some other stuff, right? Equipment. Like for example, these are platters. There's a motor in between. So these spin, and then you have a moving arm with a head, a reading head that reads the data on these, right? And of course, SSDs are typically they are on chip. They are like a chip that you can read and write data from, right? There's no memory cards are things like this, right? So this is one of the most famous memory cards, SD cards, right? But you can also Sony, right? For example, have memory sticks, right? Olympus has their own XD card, 3.5-inch floppy disks where you could take 1.44 megabytes of data, right? Not used anymore. I don't even think you can. And these are 5.25, which are even smaller. These are your pen drives, right? And these are your optical discs because it uses laser, right? It uses optics, right? Laser light to read the content on the drive, right? So these are your secondary. And if you take these as offline, things that are portable, like your external hard disk or portable hard disks, your DVDs, your memory cards, your pen drives, they're all offline or portable storage, right? Okay. So now we've talked about the CPU being the brain of the computer, the memory is inside the computer, and the hard disk is typically inside the computer as well, right? Now we talk about peripheral devices, devices that are around the computer that help the computer either read or data into the computer, or it helps the computer to output information or data or information or some sort of form like that. And the third device is communication devices that helps computers communicate with other computers or devices. So the first type of device is called input devices. These are the devices that basically get data into the computer. And if you look at it, right, this device is called the QWERTY keyboard. Why do you call it the QWERTY keyboard? If you look at this first line of characters, QWERTY, call it the QWERTY, right? QWERTY keyboards came from typewriters. So QWERTY keyboards are actually not optimized for typing. They actually want to make you slow down, right? QWERTY layout makes you slow down when you type. It's not because of the limitation of the computer, it's the limitation of the typewriter. And the people who started typing on computers mainly were people who used typewriters. So they didn't want to learn a new keyboard or a keyboard layout. So they still kept the QWERTY keyboard. And ultimately, now the QWERTY keyboard has become the standard keyboard, but it's not the optimal keyboard. So you can always design a better keyboard or a keyboard layout if someone is willing to use it, right? And the next device is called the pointing device or the pointer devices, right? And During our time, we had what's called the ball mouse, right? So you had a covered in rubber and two wheels that used to rub against it. So when you move it on the desk or something, this ball rotates and it tells the computer which way the pointer needs to move, this way or whether the pointer moves that way, right? Uh, the problem with this was basically it gathers the little ball and these rollers gather dust and then it doesn't work properly. To avoid this, they invented what's called the optical mouse. It uses a light, an LED, and a sensor that picks up a tiny difference of how the surface, which is illuminated by the red or green or blue light, how it changes and it decides which way the mouse is moving and then which way the pointer needs to move on the screen. If you take a ball mouse and you turn it upside down, you end up with what's called a trackball. Now, why do you need this? You see, the mouse needs a space to move. You move the mouse around, right? But a trackball doesn't move the mouse, it moves the ball. So you can be and still move your fingers to move the mouse pointer or the pointer on the screen. So the pointer is this. Now, in this case, it's a pencil, but it's typically the arrow on your screen, right? That's called the pointer. And then, of course, nowadays, if you have laptops or stuff like that, you have the touchpad or the touch trackpad or the touchpad or the trackpad, right? So this is also an input device. The third kind of input device, touch screens are something very unique, right? Because you see, when you use the mouse or the keyboard, you're only giving an input. But if you look at a touch screen, the touch screen gives an output as well. So it's actually an input-output device because you see a picture that the computer is giving you, and you can also move stuff around, touch, you can press buttons, you can do different things. So you can give commands to the computer as well as see information that is being output from the computer, right? So they're called touch screens. If you play computer games and you want to fly a plane or something, a joystick, right, would be a tool, right? And certain computers like old Lenovo computers, right? What they were called IBM. Yeah, they were called IBM computers. Now they're called Lenovo, right? These computers had a little button. It's called a nipple mouse or a isometric joystick, where you can move this and you can make the mouse pointer go this way, that way, up or down, right? And another type of interesting for us is the digitizing tablet. If you're like interested in digital art or something like that, right? Drawing stuff. So you might draw stuff on a paper or something, and then you want to uh, bring it onto the computer. Nowadays, of course, you can scan it and then you can use a tool like Inkscape or something to vectorize it, right? But if you want to draw something, you can also use a digitizing tablet. So it uses something called a stylus or a pen, right? You can use this as a instead of your finger to be more precise, right? So you can use these kind of things. So digitizing tablet basically inputs information back into the system. Right? And then you, of course, have these different types of cameras which capture images. So they may be still images, right, like a digital camera, but you can also capture moving images, which we call video, right, on a webcam or a camcorder or even a DSLR camera, right? So this is a way of inputting images into your computer. Another way of inputting images is, of course, the scanner, right? We call this a flat bed scanner, right? Because it scans documents, right? And this one is called a 3D scanner. So if you want to take this, whatever that is here, and you want to make a 3D model of it inside your computer, you have to use what's called a 3D scanner. right? And then you also have other tools like Kinect, Microsoft Kinect, which can actually scan when you're jumping around or moving around. It'll find your head and your hands and your feet, right? And it can do a 3D scan of you as well, right? And of course, you see ultrasound, ultrasonography, right? Ultrasound scans, right? MRI scans, magnetic resonance imaging. They are all the sensors that basically can get an input based on various factors. So this is how, so this is basically a baby, right? When sound waves, ultrasound waves bumps off this baby, there's another sensor that sensors it and then creates an image, right? This creates various slices of uh, how your body's fluids and all of that are there according to magnetic resonance. And then it puts them together to create a three-dimensional uh, image, right? So the other one is typically what we use. If you go to get your passport or something like that, right? Or if you go to get your driver's, I don't know, driver's license, I think, yes. And even your national ID, you have to give your fingerprints, right? So you have fingerprint scanners. Uh, you see, there's something called an iris scanner. It's the back of your eye. It scans, and these are more accurate in a sense. They are more unique to individuals even than the fingerprint. So iris scanners scan the back of your eye, right? And then if you go to a shop or something, you will see that some of them have barcode scanners, right? And this is what I said. If you want to capture data using your body movements and things like that, you can use the Move or the Microsoft Kinect, right? Okay. So if we go to the output devices, the main output devices that we use in computing is your display, right? So you have CRT or cathode ray tubes, right? These displays, we call them flat, not sorry, fat monitors because they used to be big, right? And they use cathode ray technology, right? They use a lot of energy and are not so nice on your eyes. Okay, but if you look at all, if you come to university, you will see these flat screens. So these are basically your LED or LCD monitors, right? LED or LCD monitors, and then if you can afford a lot of money, you can also have OLED monitors. So these are LCD and LED monitors, basically LED displays. They use a screen, right, that have what do you call liquid crystals that react to certain voltages. OLED displays basically have LEDs. Each pixel is an LED, right? And it gives you a lot of very high contrast, real life color, right? But they are extremely expensive. And then you, of course, have these projectors that you can project images onto the screen, right? And then, of course, those are images, right, or videos. If you want to hear stuff, you need speakers, right? So you need speakers. If you want to put it over your ears, you call them headphones. If you want to put it inside your ears, you call them earbuds, right? If they have a wire, you call them wired. If you don't have wires, you call them wireless, right? So they're for audio. Now, audio, you can't touch audio, can you? No, you hear it. Can you touch what you see? No, you can't. But if you really want to touch something, right, you have to print it out. If you want to print things like receipts and things like that, you use dot matrix printers. If you want to use ink to print, you use bubble jet or inkjet printers. If you want to use, if you want, like the problem with bubble jet and inkjet is if you get water on it or something, it typically runs, right? It blots. But laser printers, if you want high quality prints, right, black and white typically, or in color as well, you use laser printers, which uses a very different technology. It uses something called toners, right? And then if you want to use what do you call, if you want to print big banners or something like that, you have to use big printers called plotters that print on a canvas. And nowadays, even in the Department of Statistics and Computer Science, you get what's called a 3D printer. You can actually print in 3D, right? So it takes in something like a plastic thread, heats it up, and then it prints it on top, right? So you can actually uh, print in 3 dimension, right? So we have one of the departments. So if you are doing projects and things, you can always get it, get something printed here, right? Right. And the final thing, peripheral device is communication devices. When we were your age, right? We were first year students. When we wanted to use the internet, we had to plug it onto the what do you call computer, the telephone line, and we had to dial a number and then connect to the internet. But now these are not used, almost not used. What we use is network cards, right? If you have a network in your home and you have a wire that needs to be connected, we have to use a network card. If you have a Wi-Fi connection, then it's wireless. But if your computer doesn't have it, then you have to use a Wi-Fi card. If your computer doesn't have slot for a Wi-Fi card, then you can use a USB Wi-Fi adapter that you can use to connect to the Wi-Fi network. Right? In the CPU, so you have a CPU socket. On top of it, you have to plug in a fan because the CPU gets extremely hot. So you have something called a heat sink and a fan that cools the CPU down. If you want to fix your memory, this is where you fix your memory, right? If you want to fix in card or a graphics card or something, you plug it in here, or a sound card, you plug it in here, right? If you want to fix your hard disks, yeah, you can do it if you have an IDE or if you have a SATA, you can do it here. But nowadays, motherboards come with a SSD slot as well, right? So you can plug in a SSD hard disk, right? And then if you want to connect outside USB, if you want to connect displays or monitors, or if you want to connect your sound, right? If you want to connect USB devices like keyboards and mouse and things like that, these are your connectors, right? So this is what typical back of a computer looks like. I'm not talking about a laptop, talking about a desktop computer. You have where your power is connected. This is your power supply with a fan, right? You have your VGA port, you can have your USB ports, right? You can have your audio ports, your network ports, and all of that, right? And if you're thinking of buying a computer, these are the ports that you need to think of nowadays. I think I'll touch on them the next lecture we have, what type of ports you need to have nowadays if you're thinking of buying a computer, right? So that as science graduates, right? So work, what they do, what their capacity is, what their strengths are, what their weakness is, right? And or advising someone to buy one, or you're thinking of you need to look for, right? All of these are each of these components actually do in a computer system is what you need to as science graduates, right? So that was of this lecture to of what is a computer, what it does, what are the components that make up a computer, right? So next week when we meet, I will discuss with you what you need to consider when you're buying a computer, because it can be very confusing out there in the market, right? On what device to get according to your requirement, right? So we'll discuss that. So Have a nice evening, and of course, you're going into the weekend from tomorrow. So have a nice weekend. I'll see you on Monday. Right. So